Hey everyone, welcome to this explainer. I am absolutely thrilled to guide you through today's topic, because we are looking at the invisible engine that literally powers modern artificial intelligence. Have you ever actually wondered how the raw, chaotic, just completely messy internet gets transformed into the pure, structured data that large language models actually learn from? Well, today, we're going to demystify that exact journey.
Okay, let's dive into this. How on earth do you prepare a multi-terabyte web corpus for an LLM? I mean, really think about it. The internet is full of brilliant articles, for sure, but it's also just stuffed with repeated navigation menus, bot-generated spam, and, recipes with 10-page backstories. To train an AI, you need pristine text, and getting there requires a seriously heavy-duty data refinery.
To figure out how this is done in the real world, we're going to use an incredible source for today's explainer. We're drawing directly from a hands-on coding tutorial by Sana Hassan, which was published on MarkTech Post. This comprehensive guide to the FineWeb Dataset is essentially going to serve as our exact blueprint for today's tour of the data refinery.
Here's our logical map for the pipeline. First, taming the web corpus. Second, streaming the FineWeb dataset. Third, filtering out the noise. Fourth, catching the near duplicates. Fifth, tokenization for AI. And finally, analyzing the final corpus.
Section 1. Taming the web corpus. Refining raw data.
Imagine the internet's raw data as wildly unrefined crude oil, right? You can't just pour it directly into a sports car. To refine it, we're going to construct a 4-step coding pipeline to clean up this multi-terabyte mess. Step 1, we stream the data. Step 2, filter for quality. Step 3, deduplicate the text. And Step 4, tokenize it into a format the AI can actually read. Let's look at how we execute this.
Section 2. Streaming the FineWeb dataset. Working with the sample 10BT subset.
So right away, we hit our first major hurdle. Trying to download a multi-terabyte dataset will instantly crash standard memory. There's just no way around it. So as our MarkTech Post guide points out, we don't download it. We stream it. Specifically, we stream a manageable, fixed number of documents from what's called the sample 10BT subset. We pull the data over the network row by row, which lets us work efficiently without completely blowing up our hard drives.
Once we stream those records, we convert them into a data frame to really inspect the dataset's underlying structure. It's like looking at its DNA, basically. We're looking at the URL where the text came from, the identified language, a language score that tells us how confident the system is that it's actually English, and the stored token count. Having all this gives us a massive head start on understanding exactly what we're dealing with.
Section 3. Filtering out the noise. Quality control.
Now, what's really interesting about this slide is how we actually separate the high-quality text from the absolute junk of the internet. Following the tutorial, we recreate simplified versions of FineWeb's quality filters using heuristics inspired by models like Gopher and C4. We check every single document for abnormal word counts, poor word statistics, boilerplate navigation text, repeated lines, and overly list-like structures. We essentially run a massive audit to summarize how many documents pass or fail these simplified filters, just to guarantee we only keep the good stuff.
Section 4. Catching the near duplicates. Removing repeated text.
Having good text isn't enough if it's copied 1,000 times across the web, right? That just causes models to memorize rather than actually generalize. To fix this, the code implements something called MinHash and locality-sensitive hashing, or LSH. Now, without getting bogged down in the heavy math here is what you really need to know. These algorithms convert documents into small overlapping text chunks, they call them word shingles, and then generate mathematical signatures for them. This lets us approximate and index near-duplicate document pairs across a massive web corpus at lightning speed. It is just an incredibly clever way to find similar texts without having to painfully compare every single document to every other document one by one.
Section 5. Tokenization for AI. Translating for LLMs.
Once we actually have clean, unique text, we have to translate it, because large language models read tokens, they don't read words. In this crucial verification step from the tutorial, we take our clean text and use a production-style tokenizer, specifically the tick token tokenizer, to recompute the GPT-2 token counts. We then compare our recomputed counts against the stored token counts in the dataset's metadata. We do this to measure the average difference and basically make sure our pipeline's tokenization is behaving exactly as expected. So, the crucial point is this. By calculating the characters per token metric,
we get a crystal clear understanding of tokenizer efficiency across our sample documents. It tells us how densely our tokenizer is packing human language into AI-readable data. If the ratio is off, well, it means the model's going to process data inefficiently.
Section 6. Analyzing the final corpus. The final polish.
We've streamed, filtered, deduplicated, and tokenized. Now we get to step back and admire our clean data. And this brilliantly illustrates one of the best ways to understand it, looking at where it actually came from. By extracting the domain names from the URLs of our clean data, we can identify the most frequent domains. This reveals exactly which corners of the internet are providing the highest frequency of quality, usable data for our AI.
The tutorial wraps up by generating some really rich visual analytics. We get these compact summaries of the token count distribution, which shows us document lengths. We see the language score distribution, proving the quality of the text. We map out the characters per token for efficiency, and we review the final filter results and duplicate counts. This data visualization absolutely proves the effectiveness of the whole workflow we just built. I want to land on this massive number for a moment, 10 billion. Throughout this whole explainer, we've been working with the sample 10BT subset. That stands for 10 billion tokens. And remember, this is just a sample of the full FineWeb corpus. Seeing this number really emphasizes the immense, practical scale of what these pipelines are required to handle when preparing data for modern LLM training.
We've journeyed all the way from a chaotic raw web stream to pristine, verified, AI-ready data using Python, streaming, and some seriously clever algorithms. It is a fascinating process that proves just how much heavy lifting happens before an AI model even begins to learn. So I'll leave you with this. Are you ready to scale this workflow and design the pre-processing pipeline for the next great LLM? Thank you so much for joining me on this explainer, and keep exploring.